All right, so in this lesson, proportionality theorems, we find ourselves back in triangles. Okay, and we're going to look at the proportions that are created by an angle bisector or a line parallel to one of its sides. Okay, so the idea being, we've seen angle bisectors before, but when an angle bisector is drawn in a triangle through the opposite side, it creates segments that are in proportion. Okay, and we're going to look at that. We're also going to look at a segment that's drawn parallel to the opposite or the third side. Now we've seen this before in midsegments. Okay, and so we're going to look at the proportions created by a midsegment, and we're going to look at the proportions created by a side that's parallel to the third side but doesn't necessarily go through the midpoint. Okay, so in each case, proportions are created. Now we're going to look at triangle midsegments here, just kind of to review, because I think it helps us understand the main idea of the lesson that we're going to cover next. So with a triangle midsegment, in case you forget, a midsegment joins two sides through the midpoint of each side, and that is parallel to the third side. Now, because it's parallel to the third side, we get congruent corresponding angles. Now, because we've got two triangles, we've got the small triangle DCE and we've got the large triangle ACB. Those two triangles end up being similar by angle-angle. So we can write that down. Write that triangle DCE is similar to triangle ACB by angle-angle similarity. Now, when we were exploring midsegments before, the main idea was on the relationship between the length of the midsegment and the length of the third side. And that relationship is 1 to 2, or x to 2x. But in this unit, we're really focusing on the ratios of sides, given that two triangles are similar. So in this case, we can say that the ratios of corresponding sides are equal. So we've got the small triangle and the large triangle. In the side CD to AC, which is the whole side of the larger triangle, so that's the ratio of a pair of corresponding sides, is equal to the ratio of CE to CB, the ratios of these corresponding sides, the short and the long, and that's equal to the ratio of the third side, DE to AB. Now we can verify that we've written these correctly in the sense that we can look at the names of the triangles. So we have the CD length to the AC length. Those are in corresponding positions. We've got the CE length to the BC length. They're in corresponding positions. And the DE length and the AB length are in corresponding positions. So all the ratios of corresponding sides are equal. Now we're going to use that fact to extend it to a segment that just crosses through two sides of a triangle and creates similar triangles. But let's go on to a couple examples from Delta Math about midsegments. Okay, so triangle TUV, that's this midsegment triangle inside, is formed by joining the midpoints of the sides of triangle QRS. So we have midpoint, midpoint, midpoint. The lengths of the sides of triangle TUV are shown. What is the length of RS? Okay, well, RS is parallel to VT. That means RS is double the length of VT. So if VT is 3, SR is 6. Okay, so this is a midsegment question, not a proportion question. But again, the midsegment idea will lead us into proportionality. So let's do another midsegment question from Delta Math real quick. This one's more algebra-based. It says P is the midpoint of MO, so we've got a midpoint here. Q is the midpoint of NO, so we've got a midpoint here. So this is a midsegment, and its length is 49 minus 8x. MN, this third side, has a length of 41 plus 3x. Now remember, the midsegment is half of the third side, or the third side is double the midsegment. So we can say that the third side, MN, is double the length of the midsegment. Okay, so we can write this now. We can substitute in these expressions for each length. MN is double the length of PQ. Okay, now we just need to do some algebra and solve for x. Okay, so we get 41 plus 3x is equal to 98 minus 16x. And we got to move our x's to the same side and our constants to the same side. So let's move the 41 over with the 98. 3x is equal to 57 minus 16x. Add the 16 to both sides. And we get 19x is equal to 57. Divide both sides by 19. Whoops. And x is 3. Okay, so this is a triangle midsegment problem, not a proportion problem, but the midsegment idea will lead us into proportions. Okay, now that idea is called the side splitter theorem. So instead of having a segment that goes through the midpoints of the two sides of a triangle, it does split the two sides, and we know that these two triangles are similar, the small one and the large one. The side splitter theorem just says it actually doesn't matter where you put that side length, or that side splitter. It could be right there. As long as it's parallel to this third side, we get similar triangles. And you can see that. If these two lines are parallel, we've got a pair of corresponding angles there. We've got a pair of corresponding angles here. So the two triangles are similar, this small one and this large one. And that's true no matter where you put that side splitter. Okay? So if you put it down here, we still have a pair of similar triangles. So let's just add some numbers here to kind of see what proportions are created. So let's say this is A and B, and C and D. Now, one thing that's going to be important in this lesson is kind of the language. And what I use is the words whole and part. And we've used those quite a bit this year, right? Part plus part equals whole. Okay, well, we've got two triangles, and A represents the whole side of the small triangle, B represents the whole side of the small triangle, and C represents a part of the whole, and D represents a part of the whole of the large triangle. Now we also have kind of this other side we can label. The entire side length is either A plus C, or we can give it a new name, E. Same thing is true over here. This entire side could be called B plus D, or we can just call it F. So when we write a proportion, we've got options. We can compare whole to whole as whole to whole. We can compare whole to part and whole to part, as long as we get these kind of the names in the right order. So this is what I mean. We can compare A is to B. What we just compared is whole to whole. This whole side length of the small triangle to this whole side length of the triangle. But we can compare that to part, C to D. This part of a whole and this part of a whole. So that's a kind of a valid proportion that can be written. But we can also compare, let's say, these sides and these sides. So we can compare a whole to a part this direction as a whole to a part in that direction, B to D. Now, one way we can verify that these two proportions are true and they represent this diagram is just by looking at the cross products. Notice these cross products give us A times D is equal to B times C. Well, what do these cross products give us? A times D is equal to B times C. So if the cross products are if cross products are equal, we know the proportions are true. But these give us the same cross products, which means these proportions have to be equivalent. Now, they're not the exact same proportion. Here we compared A to B, and here we compared A to C. So they're not the same proportion, but they're equivalent proportions because they lead us to equal cross products. Okay, so write the official side splitter theorem here in your notes. It's also called the triangle proportionality theorem. Okay, so if you were to Google the side splitter theorem, you might get something that says triangle proportionality. They're the same. So our definition is, if a line is parallel to one side of a triangle and it intersects the other two sides, okay, so TU is parallel to QS, and it intersects side RQ and it intersects side RS, then it divides the two sides proportionally. Okay, let me just give some colors here to demonstrate. We've got this whole piece, and we've got a short piece. On the opposite side, we've got a whole piece, and we've got a short piece. And so what this says is RT is to TQ, this whole length is to this part length, as RU, this whole length, is to that part length. Now you can make any kind of comparison. You can go whole to whole is part to part. Okay, you can write that proportion. Or you could say part to whole is equal to part to whole. Okay, so let me show you some of those proportions you can write in this next slide. Okay, so use the diagram to complete each proportion. You should write this down in your notes just so you get an idea of what proportions are true. Okay, A to B is a whole length to a part. So we got to make sure we write a whole to a part. In this case, C to D. Okay, A to C. Well, this time we're comparing a whole length to a whole length. And now we've got kind of two choices. We could compare part to part, or we can compare whole to whole. Okay, so A is to C, whole is to whole, as let's say part is to part. Now D is to K. Let me erase what we've got here. So D is to K. Well, now we're comparing a part to a whole side. So a part is to whole as a part is to whole, as B is to J. All right, so here's 3 examples for you to try. Put these in your notes, and if you want to check your answers with me in class, just come see me. All right, so let's look at an example from Delta Math. In the diagram below, angle PNO, that's this angle, is congruent to PQR. Okay, so we have 2 congruent angles. Solve for x. Well, if these 2 corresponding angles are congruent, we know that these 2 lines have to be parallel. Therefore, QR is a side splitter, and I'll just write that. QR is a side splitter. Therefore, the ratios of these sides are congruent. The sides that it splits, those parts and wholes are congruent. So we can compare, let's just say, 28 to x, that's a whole piece to a whole piece, as 14 is to 7, part to part. So 14 is twice the length of 7. 28 is twice the length of what? 14. So you can see 14 is to 7 as 28 is to 14. That's a ratio of 2 to 1. This is a ratio of 2 to 1. All right, let's look at another side splitter problem from Delta Math. Now this one, it's essentially the same idea. They just give everything to you in words. All right, so angle SQR is congruent to STU. Therefore, these lines are parallel. Therefore, ST is a side splitter. Now, it's not a midsegment because it doesn't say anything about U being a midpoint, but it is a side splitter. And ST is the length of 32.7. SU is 23.3. TQ is 16.3. Find the length of UR, we'll put an X. Okay, so let's write our proportion. And this time, we'll just compare whole to part on the top as whole to part on the bottom. 23.3 is to x as 32.7 is to 16.3. Okay, so we're going to cross multiply and divide, and we're going to get 32.7x is equal to 379.79. And we're just going to divide by 32.7. Now this is probably going to give us a decimal answer, and it says round your answer to the nearest tenth. Okay, so 379.79 divided by 32.7 gets us 11.6 when we round to the nearest tenth. All right, let's continue. Now this is one I definitely want you to put in your notes. It says, be careful, because there is a case here that it's easily done wrong. The wrong proportion is written. You might say, well, why? Well, it's when the distance that you're given is on one of the parallel lines. Notice on the last couple examples, none of the distances were given on a parallel line. Okay, so I didn't give you any of those distances. It's when the distance is on a parallel line, in this case, that problems arise. And I'll show you the wrong proportion. Okay, and you might say, well, 7 is to 5 as 14 is to x. Okay, and so what's wrong with that? 7 is to 5 as 14 is to x. It seems reasonable. But let's go back and use those words whole and part to kind of compare or to show what we're comparing. 7, I'll write this in different colors. 7 is a whole length. 5 is a whole length. Okay, so in other words, we've got this triangle here, and 7 is a whole length of that triangle. 5 is a whole length of that triangle. So we made a whole-to-whole comparison. Well, let's come over here. 14 is to x. Well, 14 is part of the large triangle side. Okay, so we've got a part. And x. What is x? Well, x is a whole length of the large triangle. Okay, well, this is an invalid proportion. You can't say a whole to whole is equal to a part to whole. They're not corresponding. You can't compare whole to whole, part to whole. So we're going to have to come up with something different. So let's look at what the right proportion is to right. Okay, now we have a whole piece to a whole piece, and then we have a part to a whole. Well, notice this side does give us the whole length. It's 21. So now we can compare. Instead of using 14 as to x, we can say 21 is to x. So whole length is to whole length as whole length is to x. Okay, it was this piece that caused the problem. Now we can just cross multiply and divide. Right? So 7x is equal to 105, and then divide both sides by 7, and you get x is 15. So just be careful if you're given one on Delta Math that has a length that's one of the parallel sides, to make sure you write your proportion in the right way. All right, so this next idea is just an extension of the side splitter theorem, and it just says if we've got 3 parallel lines that cross 2 transversals, okay, and let's just say this is line A, B, and C. Well, these 2 transversals could potentially, let's say, keep going and meet up here, and they'd form, let's say, the top of a triangle, and these 2 sides here could be connected anywhere. I mean, they could be connected right here, and you'd have a triangle. Well, anytime you have parallel lines splitting transversals, you still get that the parallel lines split these sides proportionally. Okay, and so let's just add some side lengths here. And let's just say it was W, X, Y, and Z. And the idea is the ratio of these 2 parts, let's say this piece to this piece, is proportional to the opposite side, X to Z. And so we can write this proportion, W is to Y, as X is to Z. Now, proportions can often be written in a different way. We can also compare this direction. So we have another proportion we could write. We could say W is to X as Y is to Z. Okay, so this is given the name 3 parallel lines theorem. At least that's one name that's, that people call it. So if 3 or more parallel lines intersect 2 transversals, write this in your notes, then the segments intercepted, okay, that's the A, B, C, D are the segments intercepted by those parallel lines. Then the segments intercepted on the transversals are proportional. In other words, parallel lines proportionally divide their transversals. So A is to C as B is to D. Or we can go across. A is to B as C is to D. Now we went from left to right, but we can also go from right to left. D is to C as B is to A. Okay, so let's see how these look with a couple examples. We're going to solve for x. We've got parallel lines splitting 2 transversals. Therefore, it divides the intercepted segments proportionally. Now this one just has this additional number here. It has no other side to compare it with. But we have those 2 sides also. In other words, 4 is to x as 1 is to 1.2. 4 is to x as 1 is to 1.2. Cross multiply and divide. So we get 4.8 is equal to x. All right, let's look at the next one. Again, we've got parallel lines that split 2 transversals, which means the intercepted segments are proportional. Now the only catch here on this one is you're given a whole length, not this intercepted segment length, but we can find it going whole minus part equals the other part. So this is a 4. 9 minus 5 is 4. Now we can compare. 4 is to x as 5 is to 6. 4 is to x as 5 is to 6. And we get 24 is equal to 5x, or 24/5 is x. Now this can't be reduced. You don't need to convert it to a decimal or anything else. On Delta Math, it'll accept it just like that. Okay, so here's an example right from Delta Math. Given lines L, M, and N are parallel. Okay, so parallel, parallel, parallel. And cut by two transversals. Find the value of x. Well, these two intercepted segments are in the same proportion as these two intercepted segments. So 16 is to 15 as 35 is to x. Cross multiply and divide. And then divide by 16. And again, this one says round your answer to the nearest tenth. We're going to get a decimal, and it comes out to be 32.8125. Now this 1 is less than 5, so we're going to keep the 8 and 8. So 32.8. All right, our final theorem is about angle bisectors. Now we've seen angle bisectors, we've constructed angle bisectors, but now we're going to look at this in terms of a triangle and what proportions it creates. And again, it does help sometimes to use some words to describe these. And in this case, we're going to use long and short, okay, just to kind of compare lengths. We've got this angle bisector. And what it does is it splits this third side into two parts. And you can kind of see we've got a long part here and we've got a short part there, or a shorter part anyway. Okay? So the angle bisector splits this side into a long piece and a short piece. Okay, and that will almost always be the case that when you split an angle, you're going to end up with a long piece and a short piece. Okay? So in this case, we have a long segment and a short segment. Now we've got these remaining two sides of the triangle. And it'll be true that the longer side is over here with the longer piece. Okay? The shorter side is over here with the shorter piece. So we can say that this long piece is to the short piece. That ratio of long to short is in the same ratio as this long side is to the short side. Okay, so long to long is equal to, or long to short is equal to long to short. Or we can say, the blue to blue is equal to the purple to purple, long to long is equal to short to short. So here's the official theorem that you need to write in your notes. Same diagram. If a ray bisects an angle of a triangle, okay, so here's your ray bisecting the angle, then it divides the opposite side, okay, and that's into a long piece and a short piece. It divides the opposite side into segments whose lengths are proportional to the lengths of the other two sides. Okay, so we can finish this statement here. If ray CD is an angle bisector of angle C, then the ratio of the long piece to the short piece, DB to AD, is proportional to the long side to the short side, BC to AC. Okay, so long to short, or long to long is short to short. So let's look at this in practice. Here's a Delta Math question. It says segment BD bisects the angle ABC. Okay, so we know that this is an angle bisector. It splits the angle. Therefore, we have a long piece and a short piece, and a long side and a short side. So we can make a comparison, and we can say, or a proportion. The long piece is to the short piece, as the long side is to the short side. Okay, and cross multiply. So 12x is equal to 144. Divide, and we get x is 12. Okay, let's look at another one. Segment BD bisects segment AC. Solve for x. All right, so if segment BD bisects segment AC, okay, here's segment AC. BD bisects that side, which makes this a midpoint. Now, if we go from vertex to midpoint, well, then if this is 12, that's 12. Notice this problem never said anything about an angle bisector. This is not an angle bisector, but it's a median. Now, medians and angle bisectors look a lot alike. A median goes from vertex to midpoint, whereas angle bisector goes through the vertex and splits the angle. Now on delta math, there's a task called median versus angle bisector, so you're going to have to be careful which one you're dealing with. If it's a median, it just splits this opposite side and goes right to the midpoint. If it's an angle bisector, it splits this side into a long and short piece that's proportional to the sides of the triangle. All right, so here's a lesson recap. We've got three big ideas: the triangle proportionality theorem, the side splitter theorem. This segment, if it's proportional to the third side, divides these two sides proportionally to those two sides. Okay, and we've got the three parallel lines theorem, which is just an extension of this, that three parallel lines through two transversals divide the two transversal or intercepted segments proportionally. So this piece is to this piece as that piece is to that piece. And then finally, the triangle angle bisector theorem. If a ray bisects an angle of a triangle, then it divides the opposite side into segments whose lengths are proportional to the lengths of the other two sides of the triangle. Long piece to short piece, long side to short side. Okay, so there's the three big ideas. Each one involves writing a proportion. Sometimes it's helpful to use the words whole and part to make sure you're comparing the right lengths, or long and short to make sure you're comparing the right lengths. And if you write a proportion and you want to make sure it's equivalent to another one, just make sure that your cross products are equal in every case. All right, so if you have any questions, obviously you can email me or ask me in class.